using random forest algorithm, and you know how exactly the weightage is calculated, right? If a feature is most of the times being the root node, that is given, you know, most weightage, and if a particular feature is in the second layer in most of the trees, then it is giving a little more, a little less, like that. So if a feature is able to distinguish data clearly, that will have less impurity. Less impure features are the most important features. So that's how tree-based, the ensemble models work. Random forest. How exactly the overfitting is reduced? If you take the complete tree, it may predict, but the prediction may be wrong for the records, for the pairs which are not present in the data. But if you do random forest, like multiple trees with columns and maybe subsets of data, the number of combinations are going to be covered more, with which the probability of having accuracy, more accuracy will improve, or getting model balanced will improve. So here the overfitting problem will be resolved by taking multiple models. These are parallel models. If you look at the bagging or pasting or random forest, they're all parallel models. You take data, you do some manipulation, either rows or columns, subsets, or both, and build a model. And ultimately, you take the all models predictions and try to take majority voting and make predictions. These models can be built parallelly and trained parallelly, right? Built in the sense trained parallelly. And then you can make predictions also parallelly. On different machines, you can do it. Right? So parallel processing is possible in bagging, pasting, and random forest algorithms. We are looking at another kind of algorithms which are sequential. Okay, the boosting algorithms are sequential, and deep learning algorithms are both parallel and sequential. Okay, they are even complex, in nature, in the ways to predict. Okay, so boosting algorithms are used only when the learner is weak. If the algorithm, if the learner is so very weak, then you go with boosting algorithms. What is the example for learning, where weak learner? In the initial classes, right, on the website, I showed you an end-to-end regression problem where the linear regression algorithm is giving only 50% or maybe see 57% maximum accuracy. Whatever we do, the accuracy was not improving. And in that case, we took gradient boosting, right? So if the learner is very weak, then you go with boosting algorithm. How boosting algorithm works? Boosting algorithms take data, try to build a model, make predictions, and on the data they make another change and try to build another model. So the boosting algorithm's major focus is going to be on the wrongly predicted data. So it takes this data, right? There are positives and negative records. It built a model. Now suppose that it's a decision tree model, and it actually made predictions, right? This is the decision boundary, and it predicted all the top records as negative and all the bottom records as positive. In this, right, it predicted these two records wrongly, this record right wrongly, right? One positive record and two negative records were predicted wrongly. If you see carefully, do you agree? And the first model, if you take this as a first model, right, this line as a first model, you passed your data and you made predictions. This is the decision boundary. Two negative records are falling on the positive side, one positive record falling on the negative side, right? So the boosting algorithm, what it will do is it will try to increase weightage for this record and these two records. What is weightage? Suppose that there are m number of records. Initially, it will give 1 by m as the weightage, right? There are 1000 records. 1 by 1000 it will take and multiply all the records and then make the predictions. algorithm is normal. On top of algorithm, it is going to assign some weightage to the records and then make predictions. Now, these two records and this record are wrongly predicted, right? While building the next model, it will increase the weightage for these wrongly predicted records so that the model's focus is going to be on these three more compared to other records. Okay, the mistake made by the first model is going to be covered by the second model. Okay, so it is going to build a model. Before building a model, it is going to give more weightage to the wrongly predicted records. See this, I made these a little bigger, right? That means the weightage given to those records are going to be more. And now another model will be built, and on that model again, the decision boundary is like this. So there is one record which is predicted wrong, and there are three records which are predicted wrong. Three negative records which are predicted wrong. Now again, the weightage for those wrongly predicted records is going to grow. That this record, it became big. These three, it became big. And now we are going to build a model again. Like this, right? We'll build n number of models. And we'll assign some weightage to each of those models. Okay, let me read through the theory and then I'll explain. Now, boosting, originally called as hypothesis boosting, refers to any ensemble model that can combine several weak learners, right? I said weak learner. Weak learner means a model that is predicting around, that is giving accuracy around 50%. If the model is giving you maybe around 60% or 45%, that is called as a weak learner into a strong learner. Boosting algorithm, this ensemble model makes a weak learner a strong learner. The general idea of most boosting models is to train predictors sequentially. Okay, each trying to correct its predecessor. Each trying to correct its predecessor. That's what I said here. Increase weightage to the record so that the algorithm will focus more on those records. Right? When the numbers in the input space and the output space are big, basically input space are big, right? Input features is big. The algorithm will try to focus there, or the equations will get calculated well on those records. Okay, there are many boosting methods available, but by far ADA boosting and gradient boosting, and there are other boosting algorithms also. I forgot the name. Microsoft has actually built those. Give me 1 second. That is also used. Yeah, light GBM, light GBM. Okay, that's another boosting algorithm. Right, when data is less and you have to get good accuracy on the data, then boosting algorithms and random forest are best options. Right, so you can try it out. Okay, so it's the light GBM is a modification of the these ADA boosting and gradient boosting algorithm. I think it's ADA boosting, modification of ADA boosting algorithm. Okay. ADA boosting is a popular boosting technique which helps you combine multiple weak classifiers into single strong classifier. A weak classifier is simply a classifier that performs poorly but performs better than random guessing. Okay. Weak learner performs better than random guessing. ADA boosting can be applied to any classifier, any classification algorithm or classification problem. Sorry, ADA boosting can be applied to any classification algorithm or problem. Because ADA boosting works on classification problems, and you actually combine multiple classification algorithms. Sequentially combining multiple classification algorithms makes an ADA boosting algorithm. So what does ADA boosting do? There is really two things it does. Training the set selection. It helps to choose a training set for each new classifier that you train based on result trees. Okay, that's what I explained here, right? So it takes the data set and makes, trains a model, makes predictions, assigns weightage, trains another model, makes predictions, assigns weightage, trains another model. That's what it does, the first thing. And once after training is happened, right, maybe 100 sequential algorithms are trained. After each classifier is trained, the classifier's weight is calculated based on the accuracy. More accurate classifiers are given more weightage, right? A classifier with 50% accuracy is given 0. Right? 50% means 0, 100% means 1, 0 means -1. Okay. If a model is giving 0% accuracy, that is -1. Right? 50% accuracy, 0. 100% accuracy means 1. Based on the accuracy, each model, the accuracy is calculated. This model accuracy calculated, this model accuracy, this model, all models accuracy calculated. Based on the accuracy, the weightage is given. Right? So when a model is predicting something using that weightage, the model predictions are multiplied. Okay, first model is given 0.33, second model is 0.57, third model is 0.42, and you multiply the predictions of the records with this. Predictions are going to be probabilities, right? So either zeros or ones. Predictions are going to. So you multiply that with 0.33, 0.57, 0.42, sum it up for all the records, right? So if a record, first record's total sum is less than 0, you say the record belongs to 0. If it is greater than or equal to 0, you say the record belongs to 1. So ultimately the model becomes like this. When you combine all these, right, the model becomes like this, graphically. Got it? How ADA boosting works? Any questions?
Yes, sir. So how many such classifiers we need to keep going after one after another like that?
That's a hyperparameter, sir. That's a no. How many is the hyperparameter? In random forest bagging, pasting also, how many is the n estimators, right? N
Okay.
estimators is the parameter. We need to play with it.
Okay.
Sir, these boosting algorithms are also based on the tree, decision trees only.
So ADA, gradient boosting is definitely dependent on decision tree, but ADA boosting we can actually change the algorithm. ADA boosting classifier takes the algorithm as parameter, but gradient boosting algorithm dependent on trees only.
Okay.
Strictly dependent on trees. Let me look at the API ones. I think whatever I said is true. Double check. Yeah, an estimator, base estimator. Right, the base estimator for which the boosting ensemble is built. Suppose support for simple weighting is required as well as proper class underscore n class underscore attributes are required. So right, these are the constraints. The base estimator is decision tree. Support for simple weighting is required. That after every model building, it is assigning weightage to the records, right? That should be there. And classes underscore and n class underscore. We have seen classes underscore attribute, right? Do you remember?
Yes.
After building model, to look at the order in which the classes have been assigned the number. So these two features should be present in the algorithm implementation. Then only you can take that as an estimator for the ADA boosting. Yeah, that's a good question. I never focused on it. So the calculation also we can actually look at it. How the weightage is being assigned. So the first step, right? There are two steps I said, right? The first step and second step. Here, those two steps are different and these two steps are different. Sorry. So here, right? How the algorithm mathematically working also I tried to put it here. So each instance weight is weight Wi is initially assigned to 1 by m. initially each record's weight is assigned as 1 by m. First predictor's weight alpha 1, the classifier is calculated using the formula, right? The alpha 1 is calculated, this is eta, right? Eta into log 1 minus r1 by r1. The r1 is calculated. How the r1 is calculated? Sigma I is equal to 1 to m wi, where yi not equal to yi cap not equal to yi. I think I know my eyes are not working. So yi cap is not equal to yi. Wherever yi cap is not equal to yi, for those the weightage is assigned divided by sigma I is equal to 1 to m wi. So this wi initially is 1 by m, right? And for all the records it's going to be 1, right? Initially, when for the first iteration, the r1's denominator is going to be 1. 1 to m, 1 by m plus 1 by m plus 1 by m plus and so on m times. It is 1. Denominator is 1. On the numerator, wherever the records are wrongly predicted, only those weights. If 10 records are wrongly predicted, right, 1 by 10 by m, right? Maybe we have 1000 records. 10 by 1000 is 1 by 100. R1 is going to be 1 by 100, right? So 1 minus 1 by 100 by 1 by 100 is 99 by 99. It is log 99, right? Is that correct? Eta into log of 1 minus 1 by 100 divided by 1 by 100. So 100 minus 1, 99 by 100. Yeah, 99, log 99. Eta into log 99. If there are 1000 records in the data set and 10 records are predicted wrongly, okay, then it is going to be eta into log 99. If 100 records are predicted wrongly, let me write it down. I think that is better. So how the weightage is being assigned, that's what I am trying to show here. So suppose that there are 1000 records, m is equal to 1000, okay, and wrongly predicted, wrong predictions. Wrong predictions are 10. Then this alpha 1 value is going to be, right, eta into log of 1 minus 1 by 100 divided by 1 by 100, right? If you take 100 here, all that, right, it becomes 99. 1 by 19, 99 it is, right? It becomes 99 after calculating. It becomes 99. Okay. Let me take another color. If wrong predictions are 100, what happens? Alpha is equal to eta into log 1 minus if 100, right, what happens to r1? R1 is equal to denominator is 1, right, for the first iteration only. Next iteration this becomes complex, okay, and numerator is going to be 100 records are wrong, right? So 1 by 1000 plus 1 by 1000 plus 100 times, it's going to be 100 by 1000. It's going to be 1 by 10, right? It's 9, log 9. That alpha is equal to eta into log 9. What is log 9 base 10 and log 99 base 10? Log 9 base 10 is 0.9542. Log 99 base 10. going to be more. Log 100 is 2, right? Log 100 is 2 and log 10 is 1, right? It's going to be, this is going to be more. This value, this R1 value is going to be more when predictions are, less number of wrong predictions. R1 value is going to be less when more number of wrong predictions, right? That way it is going to calculate this alpha, and this eta is the hyperparameter that actually helps you, fix the overfitting, underfitting problems. Okay, this number, right? Whatever this eta into log 99 or eta into log 9 is the number multiplied with the wrong records. Okay, that is given more weightage, right? If the less number of records are predicted wrongly, those records are given more weightage. If more records are predicted wrongly, weightage is given, but not as big as the one we are giving there. Okay, so the boosting algorithm's main responsibility is to highlight the wrong predictions of the previous model. Right? There are multiple sequential models. The main purpose, main focus of the boosting algorithm is to highlight those records, build a model, highlight those records, build a model, highlight those records, build a model, so that those records are correctly predicted. So previous model's error is being corrected on the next model. That's the boosting algorithm. When we look at gradient boosting, right, we'll understand it better. So like that, each iteration we calculate alpha, each instance wi, where w is equal to wi, if that 1 by m is assigned to the records which are correctly predicted, eta log 99, when 10 records are wrongly predicted, eta log 99 assigned is what is, wi 1 by m into exponential of eta log 99 is the weightage, right, given to the records which are wrongly predicted. Okay, again build a model, calculate alpha 2 r2, right, again assign the weightage alpha 3 r3, again assign weightage, like that it's going to be done. Okay, and to calculate these values and all that, right, ADA boosting uses some technique, SAMME, some technique, and there is another variant also, .r. We can specify that while building a model. Right? The algorithm which should be used, we should be, this is like RBFGS, LBFGS, right, in the softmax regression classifier. If you spend time, right, this is a research item. If you want to spend time, you can spend, but I never looked into it. Frankly speaking, I don't know, okay, how exactly this algorithm works and all that. But for interview purposes, this is not needed. If you want to build models, right, you need to know how to play with the hyperparameters, and this is not that useful when compared to the deep learning techniques. So that's where I did not focus much. If you have time, you focus on it. Okay? Maybe this is rude, but um, we cannot cover everything in 4.5 months, right? So that's the problem there I'm facing with. Okay, I hope that is okay. Right? So ADA boosting algorithm I am creating here using decision trees, and you take max depth less when you are creating ADA boosting algorithm, because ADA boosting algorithm's main purpose is to make the weak learner stronger. When depth is low, the model is going to be weak. Do you agree? Depth is low on a decision tree, the model is going to be weak. Do you agree with that statement?
Yes, sir.
Sir.
Right? So we have taken a weak learner and trying to make it a strong one. And the learning rate, right? It works like um, the learning rate is to converge faster. Sorry, not, I said overfitting, underfitting, but the learning rate is to converge faster. If the model is overfit, diverging, right? You need to reduce it. If the model is converging, you need to increase and see how fast we can make the model converge. This is like learning rate in our gradient descent algorithm. Okay. So I looked at accuracy, I've got 88%, not that great. Right? On the random forest, we have got 92%. Right? So that's the ADA boosting. So quickly I will move on to the gradient boosting. The ADA boosting algorithm is used on classification problems. Gradient boosting is used on regression problems. Okay. So just like ADA boosting, gradient boosting also works, but gradient boosting actually takes trees only. Gradient boost regression trees, GR, GBRT. They call it as GBRT. It's a tree-based algorithm. How it does? Suppose that there is one input variable and there is one output variable, right? X and Y. Only one input variable. Okay. I built a tree and made predictions and then calculated errors. Okay. These are the mistakes done by the first model, right? So I take this value as the Y for the second model. See, X did not change. Do you see this? X did not change. Y changed, right? On the first model, I took original Y and tried to build a model. There is this much error. What is the error? Difference between the Y and Y cap, right? So now in the second model, I am trying to predict Y cap error, right? I am trying to correct the error, or in a way, right? If I try to predict this error, I try to build a model, predict this error. If I am able to exactly predict it, right? I can take this model, make prediction, this model, make prediction, sum these two, I'll get the exact value of Y, right? Do you agree? Did you get my statement there? Should I repeat? Shall I repeat?
Sir, okay, just let me just put my understanding.
Yeah.
In the first, you're trying to predict the Y and
Yeah.
then calculate the error, and then you are doing the predictions for the error, not the actual Y. Is that so?
On the second model, I am trying to make predictions for the Y error, not the Y.
Yeah.
Suppose that the statement I made is on the first model we know that there is this much error, right? We took this as Y and tried to build a model. Suppose that if the model exactly predicted zero error, you got here on the second model. If you get zero error, right? Suppose that on the second model you got zero error, right? If you take the record, if you take X and pass it to first model and pass it to second model, sum those two, will you get the Y correctly, exact Y?
It's like Y1 plus Y2, sir.
Prediction Y1 plus prediction Y2. If the second model's error is zero, prediction Y1 plus prediction Y2 is equal to Y1. If the second model's error 2 is zero, take that error 2 is zero.
Yes, sir.
Right? Do you agree? Any question on that? That's the key. That's the key for this gradient boosting. Any questions there? Yes, no? Everybody got it?
Yes, sir.
Right? So that's the key, right? So you build a model, you take the error and try to, so the hope is that the second model will give you zero error. No, it is not giving. So we took the second model's error and trying to build a model and try to predict it. This is also not giving zero. Like that, you will build n number of models and try to take the predictions of all the models. Y1, prediction Y1, prediction Y2, prediction Y3, and so on, prediction n number of models, and make that as the ultimate prediction. Got it? That will actually correct the error. The first model made error and second model tried to correct it. Second model made error, third model is trying to correct it. Like that, the correction, right, will sum up. All the predictions will sum up to the original Y. So let me show you that. So I took the data, built a model, took the error 1, built another model, took error 2 as the model Y value, again built a model, error 3 has y value, I built another model like that I built. And ultimately what I am doing, prediction y1 plus prediction y2 plus prediction y3 plus and so on, prediction y4 is equal to final model. If you take n estimators is equal to 4, then 4 y predictions are going to be final prediction. So final prediction and y1, the original y are the ones we are going to look at, and calculate the error, ultimate error. The model, if you say n estimators, it will do all this, sum all the predictions and give you this as the prediction. And then you do MSC or RMSC or whatever error metric, R1 score, R2 score, you calculate on these two. Got it? How gradient boosting algorithm works? Got it?
Yes, sir.
Simple, right? And idea is simple. Right? When you expand it, right, you may not be able to understand, but idea is simple. If the second model gives you zero error, that's it, right? Whatever the gap the first model is having, second model is covering it. You sum these two, you get an exact y. So that's the analogy. That's the idea behind the boosting algorithm. The first model's error, second model is trying to correct. Okay. So I have actually taken some example here, I think. Give me 1 second. No, I didn't took it. Previously I used to show a code example of building a tree-based algorithm and all that. No. So gradient boosting algorithm here, and max depth I have taken 2. Max depth means it's a decision tree only, and n estimate is 200. Learning rate 0.1, and random state is 42. X and Y, I actually, whatever the data I am showing here, I think I took the same data here. Right? This data is generated data, and I took the same data and I made predictions here. These are all the predictions I made using the data here. Okay, and then fitted the model and use that to make the whatever. Right? So here I am plotting, different. Um, um, for different learning rates and different um, estimators, right? N estimators is 200, but learning rate is 1. The model is overfitted. The learning rate is 0.1. The model is kind of best fitted. I think no, this is not to make the model converge faster. Sorry, learning rate is to fix the overfitting only. Whatever I said is true. The number is high, the model is going to overfit. It is like C on the SVM and max regression classifier. Okay. So if the number is high, the model is going to overfit. If the number is low, the model is going to be underfit. Right. This is kind of generic. I am saying this is overfitted. Do you know why? I am saying this model is overfitted. Do you know why?
It is trying to join each and every point.
It is
Yeah.
trying to predict well on the train set. It may ignore generalization. So, this is like a little generalized. It may actually work well on the train set, test set also. Well, okay. So that is the ensemble models, right? From tomorrow, we'll start with regular expressions, a little bit of NLP introduction, and we'll get into the bag of words and information retrieval. Very important concepts. Before we apply algorithms, we should understand how to convert text into numbers. Okay. From tomorrow, classes are very important, and many people are not joining the classes. I don't know why. For today, right, I'll stop because yesterday night I worked till 3 o'clock.